Today, we are glad to have Dr. Evangelos Farantatos from the EPRI. So Dr. Farantatos got his diploma in electrical engineering and electrical and computer engineering from National Technical University of Athens in Greece back in 2006, and his master and PhD degree from Georgia Tech in 2009 and 2012, respectively. So he is a senior principal team lead with transmission operation and planning R&D group at EPRI, California. So he is managing and leading technical work of various R&D projects related to synchronous technology, synchrophasor technology, power system monitoring and control, power system stability and dynamics, renewable energy resources modeling, grid operation, protection and control with high level of inverter-based resources. Dr. Farantatos is a senior member of IEEE and member of the NASB leadership team. So with that, let's get it off to Dr. Evangelos. So Evangelos, back to you.
Yes, thanks, Said, and hi everyone. And Said, thank you for inviting me to give this presentation to the Washington State University Power Group. Today, I will be talking about oscillations, different topics around monitoring, analysis, and mitigation. So I will give a background on kind of the state of the art and conventional technologies around oscillations, and some of the research we do at EPRI, and which is kind of the industry trends around this topic. Now, before going into the technical discussion, I wanted to introduce also EPRI for those who are not familiar with the Electric Power Institute. We are an independent organization, and basically we provide objective and scientifically based results that address reliability, efficiency, affordability, health, safety, and the environment. We are a non-profit organization with the objective to serve the public benefit. Our mission is to advance safe, reliable, affordable, and environmentally responsible electricity for society through global collaboration, thought leadership, and science and technology innovation. And we have a collaborative business model working with pretty much everyone in the industry, with academia, vendors, manufacturers, other researchers, national labs, and independent consultants. So that's a quick overview about EPRI. Now, regarding this presentation, the outline, I will start with some background material about oscillations, different types of oscillations, natural, forced, and then I will mention also some background material about synchrophasor technology and Phasor Measurement Units. Most of these should be nothing new to you. I'm sure you have taken classes related to these topics. And then I will go into some of the research topics that we are working here at EPRI. One topic is on wide area oscillations damping control, some work we have done around that and some case studies. Also, I will discuss more about forced oscillations and how we can mitigate them, different methods and tools we are developing. And also another topic is again related to mitigation, but now using IBR, which stands for inverter-based resources. And then at the end, I have one slide for this concept that we promote as a grid damper. And there is also a YouTube video there that I'm not sure if we will be able to play, but I can share the slides with you, and you can see how we are some high-level information about the technology we are working that we call a grid damper. So that's the outline, and again, I will start with some background material. First of all, regarding oscillations, oscillations is a significant threat to the power grid. Oscillations is not something new, but what we are seeing is that we are experiencing more severe, complex, and frequent oscillation of different types, especially given the increasing integration of renewable energy systems and the changes that are happening in the power systems, especially in the generation mix. In this slide, you can see some graphics around oscillations. And what you can see on the right-hand side is a playback of some measurement data from an event that happened in 2019 in the Eastern Interconnection. This was a forced oscillation event, and these are data that are captured from the FNET system that is developed by University of Tennessee, Knoxville. And you can see how the oscillations are propagating through the system and how the entire Eastern Interconnection was affected by that event. And we will discuss more details about the event later. Now, one category of oscillations is what we call natural oscillations. And natural oscillations, and in particular electromechanical oscillations, this is an inherent property of power systems because power systems are a dynamic system. So any dynamic systems has this oscillation mode, and as I mentioned before, this can be a significant threat to the power grid. You can see on the left-hand side some events that happened in the past. Very well-known 1996 WEC oscillation event that has been studied a lot. Let me get the pointer. Another event that happened in 2017 in continental Europe, where you see there were two generator disconnections that basically resulted in those undamped oscillations that were kind of problematic for the system. And as I said, the oscillations is not something new. We have been studying oscillations for many years now. You can see, for example, an ERIC report here that basically analyzes the oscillation modes in the three interconnections in the United States. And similar analysis has also happened in other places in the world. You can see here in this figure the common modes that continental Europe system has, basically one from north to south and two modes from east to west. Now, another category of oscillations is what we call as forced oscillations. These are sustained oscillations that are happening or can happen due to equipment failure, different inadequate control designs, and in general, abnormal operating conditions with different equipment, for example, for generators. And PMUs and synchrophasor technology are very critical in the ability to identify, monitor, and mitigate those forced oscillations. On the top right side, you can see a screenshot from a NERC report. It's a little bit old in 2017, but discusses about different methods for monitoring and mitigation of forced oscillations, and also identifies different events. And there were 24 major events that were reported in that report. Forced oscillations are happening very often, and again, we started seeing those more often. In last year in WEC in Southern California, there was an event associated with a battery energy storage system, and also the event that I discussed before in 2019. This was a 0.25 hertz event that was initiated by equipment failure in a generator in Florida, and propagated in the entire Eastern Interconnection, as I showed before the video from the FNET system. And There is another NERC report that is included in this slide here, a screenshot. You can refer to that report for more details about what happened in that event. Now, another type of oscillations, or I would say subcategory of oscillations, is what we call subsynchronous oscillations. So these are oscillations that are usually in the frequency band of 5 Hz to 50 Hz. That's why we call them subsynchronous. And especially subsynchronous oscillations due to inverter controls is of high interest. Again, this is due to the decarbonization and changes in the generation mix with increased integration of inverter-based resources. We start seeing and we expect to see and observe more often these kind of phenomena due to either control interactions or resonances with the network. You can see in this slide a few examples. An event in 2021 that happened in Scotland with 8 Hz oscillation, and since then there have been additional events in the United Kingdom, and then another event in California. I believe this was a couple of years back, related to a PV plant, and also a similar oscillation around 7 Hz. Now, related to phasor measurement units, you probably know that PMU is basically a device that measures synchrophasors, and PMU can measure voltage and current synchrophasors, frequency and drop-off. And a PMU can be a standalone device or a functional unit within another physical unit, for example, a protective relay. And then PMU collects measurements from the potential transformers and the current transformers, and calculates and provides these synchrophasors. So as I mentioned before, synchrophasors and PMU technology have proven to be critical in monitoring and analyzing and also mitigating those oscillations. And different kind of oscillations. This slide provides more information about the synchrophasor technology and compares PMU measurements with SCADA. So you can see that one main difference is the resolution. Typically, PMU data reported at from 10 to 16 records per second, compared to SCADA data, which usually we have one record every 2 to 4 seconds. Another main difference is the time synchronization. As you probably know, synchrophasor data are time stamped using a precise time. Now, as I said, PMU technology and synchrophasors have been very critical in monitoring and analyzing oscillations. And there are different ways that this can be done. It can, let's say, the low-hanging fruit is doing offline analysis of past events. So in that case, we use recorded PMU data to analyze oscillations and characterize the oscillations in terms of what is their frequency, what is the damping ratio, what are the modes of oscillations, so basically what is oscillating against what. And again, this is pretty common, and you can see here another example from a NERC report in 2019, where they basically did analysis of the 3 interconnections, the oscillation modes in the 3 interconnections in the US using recorded data. Another type of analysis that can be done is a real-time analysis. And there are also 2, let's say, categories in this case. One is what we call bring down or event analysis. So basically, once an event happens, we can use real-time PMU data to analyze the event and again calculate different indices like frequency, damping, and mode shape. But it can be also done with ambient data. So when the system is operating in normal operating conditions, we take advantage of the small perturbations in the system, and basically analyze that with different techniques, and calculate again different indices like frequency, damping ratio, etc. And this is, for those who are familiar with this, this is usually referred to as a mode meter. And as I said, there has been a lot of work in that area, and WSU is also, I have to say, one of the main contributors in this area, especially Professor Mani has done a lot of work on that. So if you are a student of Professor Mani, probably you are working on this area. And there are also many vendor tools that have the capability of those analytics for both offline and real-time analysis. So you can see a screenshot here from a specific tool. Now, I wanted to say a few things about mitigation, and one technology that we have been working at EPRI for a few years now, and it's focusing on a controller to provide damping of wide area oscillations, of inter-area oscillations using PMU measurements. And the idea here is to have a closed loop control system where basically we use PMU measurements across the system, and then we feed those measurements into a controller, and then the controller is taking decisions or generates control signals that go into different actuators, and basically modulate the active and reactive power of those actuators to provide the damping of the oscillations. So this is an application of synchrophasors in closed loop wide area control, which is not, I would say, very advanced at this point. For now, synchrophasor technology is mostly used for monitoring and analytics, not in control yet, but this is where the industry trend is going, and we expect to go. So a few more details about this wide area oscillations damping controller. Basically, this is a real-time controller that, as I mentioned before, works in real time. You get measurements from the PMUs, and then there is an analysis of those measurements through a measurement-driven model that generates the control signals. However, to set up the whole system, there has to be a design stage or an offline stage where for the particular system that this is applied, we have to do what we refer as modal analysis. So we need to study what are the oscillations modes in that system, and decide on the target mode or modes, multiple modes that we want to mitigate through the controller. And then we need, as part of the design, we need to select what are the optimal observation signals. So the PMUs are providing input signals to the controller. Then what is the optimal actuator, one or multiple actuators in the system to provide the damping. It could be different options. It could be generator, it can be a fax devices, HVDC, inverter-based resources with power electronics, including battery energy storage system. So once we have that, once we define the input signals and the output signals, we go through the some model identification process, and then we verify the control design, and then we can test that and demonstrate that through simulations and also hardware in the loop before going actual in the field. So this is what we have done. For example, here in this slide, you can see that we have developed software tools and software models for testing and applying and demonstrating this wide area damping controller. We have done this in different commercial tools, for example, PSSC and Power Factory. We have also done implementation with hardware. So we have used a general hardware platform, in particular the National Instruments Compact Trio, and we have programmed the controller to basically do or perform this control function. This is not, very simple. It's not like you get data, you do a simple analysis, and you get an output. There are many things that need to be considered, including how do you handle missing data, how do you handle delays in the measurements, and what happens if you have one of the PMUs or one of the actuators, for example, they might have a failure. So we have also supervisory control that can switch between different PMU channels and between different controllers. So all these modules here, which we kind of split into two categories: the basic modules, which are, you know, the receiver of the data, the controller, which is kind of a lead-like structure, the D2A conversion from digital to analog, and then we have advanced modules, as I mentioned, detecting delays, compensating for the delays, handling missing data, supervisory control. Again, all these are part of this packet of the implementation of the controller into the hardware that we have done, that we have done and demonstrated. This is how it looks in hardware in the loop setup. So basically, we have a real-time simulator. It can be RTDS or PAL-RT or something else. So we have a model of the system in this real-time simulator, model in the real-time simulator. We generate analog signals from the locations where we assume that we have PMUs, that we use the measurements as an input to the controller. We pass those measurements to an amplifier, and then we feed them into actual hardware PMUs that generate the synchrophasors. And then the synchrophasors go into the controller as an input. And as I said in the previous slide, we do all this analytics with the controller. We generate the control signal, and that goes back into the real-time simulator and closes the loop. And basically, we modulate again the active and reactive power of the actuators to dump the oscillations. Now, within this setup, we also have this blue box, which we call, which is basically a communication network simulator. So we use that to emulate realistic operating conditions or communication failures, for example, missing data, bad data, but also this is how we introduce delays, additional delays on top of whatever inherent delays we have in this hardware setup. So we have done different case studies at EPRI with different EPRI members, and both in simulations and also hardware in the loop. I'm summarizing here some of them. One is with New York Power Authority, one is with Terna, the system operator in Italy, one is with Saudi electric system, and then one for the National HVDC Center in the UK. Each of these studies had something unique regarding what was the objective of the study. So, for example, for the NIPA system, one unique thing was that we were studying two modes. So we had to ensure that the controller we use can basically coordinate the damping of two oscillations for oscillations for two modes. And we use different actuators, including STATCOM and generators. In the Italian system, the actuators we use are synchronous condensers. And if you remember in one of the initial slides where I was showing this 2017 event, this is what we have been focusing on through simulations and hardware in the loop. We have shown how we could have prevented this event if we had that system. In Saudi, the focus was on system separation, how we can use the controller to prevent system separation between west-south and center-east, and we were using STATCOMs and generators. And then in the UK study, we were looking into the future with high levels of inverter-based resources, but also with multiple HVDCs. and actually HVDCs were the focus here in terms of the actuator. So we were using HVDC links to mitigate oscillations. We have gone beyond simulations and hardware with Terna, the system operator in Italy, and basically we have a field implementation that we are now testing as we speak. So in this case, the architecture is as follows. We have PMUs from different locations in the system that we bring the measurements into the control center. Now in the control center, we have the controller implemented as a software controller in OpenPDC as a DLL, as an actuator, as an adapter, sorry, in OpenPDC, if you are familiar with this open source tool. So we generate the control signal centrally at the control center, and then we communicate that control signal down to the substation where we have the actuator, which is a condenser. And for now we have one condenser, or actually we have two condensers, and we have tested those individually, but we haven't done tests yet combined. But we generate the control signal, we send it to the substation. At the substation, there is another device. You can think of it as an enhanced PMU that receives the control command and then generates the control signal, analog signal that goes into the condenser to mitigate or to modulate the reactive power. And this is basically how we could close the loop and we do the experiment. So this is, as I said, work in progress, and we are very excited about that. That we have managed to go into the field and done field experiments, and hopefully we will have more to show later this year or next year with actual results from the demonstrations. Now, what I have been presenting for the last few slides has been focusing on inter-area oscillations, and I want to switch gears a little bit and focus a little bit more on forced oscillations in the next few slides. So as we discussed before, forced oscillations is another type of oscillations that can happen due to typically equipment malfunctions. The ultimate way to mitigate oscillations, forced oscillations, is to identify the source and isolate the source from the network. However, if that takes time, or if someone doesn't have the appropriate tools to do that, then another way to try to mitigate to some extent the oscillations is to implement controls to basically reduce as much as possible the magnitude of those oscillations. With this as the objectives, to basically the mitigation of forced oscillations, we have been working on different technologies. One of those is a software tool that can identify the source. So help system operators in the control room to identify the source when basically a forced oscillation event happens. And then if and when the source is identified, it can be disconnected from the network to mitigate the oscillation. So we have a tool that basically inputs the PMU data and then analyzes those and provides you with estimates of the source location. Actually, we have two versions of the tool. One is offline analysis for testing and analysis using recorded data. We have another tool that we developed this year that is an online version, which basically can input streaming data and produce this analysis in real time. These are some results from some test cases. I won't go into the details. I just want to mention that the tool has different methods of identifying the source. One is what we call dissipating potential method. Another one is very simple, that is based on the oscillation magnitude, and another one that is based on the oscillation mode angle. Each of those methods have their own advantages and disadvantages. That's why we have all of them in the tool. We have different weight factors that we can use depending on how much we trust each one of those, depending on the particularities of the system. So there's a lot of flexibility to play and customize the tool for a particular system. Now, as I said, if someone does not have tools like that to identify the source, another way to try to mitigate the forced oscillations is by suppressing them. And in order to suppress them, we need to apply some kind of control to minimize or reduce the magnitude of the oscillations. So what we have been studying is how we can use batteries and basically modulate active and reactive power from batteries to mitigate forced oscillations. So we have demonstrated that and implemented that through simulations. Actually, what we did is we replicated the January 11, 2019 event that I showed before. So basically, in that case, we played with the governor model, and we were initiating the fast valve of the governor every 4 seconds. So that created the 0.25 Hertz oscillations that happen in reality. And then using that, the data from that replicated event, we studied the different scenarios for application of the controller through the battery system. So in the top line, you can see cases where we have the source of the oscillations is in Florida, and then we have the controller also in Florida. So in that case, you see if there is no control, you can see here the red color that we have high oscillations in Florida that propagate across the system. Now, if we have a controller in Florida, so close to where the source is, then basically we can mitigate those oscillations. So you can see blue and light green colors here, which means that the magnitude of the oscillations is small. Now, if we assume that there is an oscillation that the source is in Asia, New England, so northeast, and then we have a controller in Florida, then we can see that we can mitigate the oscillations where the controller is, so in that case in Florida, but since the source is in the northeast, in that case we cannot do anything. So the bottom line or the main conclusion from this analysis is that if you have a controller close to where your source is, you can basically take care of the system and the oscillations in your territory. Now, if you are the system that is creating those oscillations, then basically you mitigate everything for the entire system. But if the source is somewhere else, you cannot do something about that. You have to rely on other actions. Now, another topic I wanted to touch upon a little bit is using inverter-based resources as actuators for providing oscillation damping. Now, there are different ways to do that. You can do that with either local data, or we refer that as local control. So in that case, we can use data from the high level, high voltage side of the interconnection of the IBR to the rest of the system, or we can use measurement data at the inverter terminal and have controllers that basically modulate the active and reactive power of the inverter-based resources to provide control, or we can have wide area control similar to what I was presenting before. So again, we have PMU measurements from across the system, we communicate those to the controller, and then we have a controller, separate controller at the IBR plant, which can be used to mitigate the oscillations. I will focus a little bit more on the local control and basically how we can implement different controllers within inverter-based resources and different inverter controls to provide oscillation damping. The objective here and the reason why we are investigating that is that we expect that in the future, when basically the number of synchronous generators in the system, connected in the system, will be minimal, then we will be losing this oscillation damping service or capability that synchronous generators have been providing so far through different controls, especially the power system stabilizer. So we expect that we will need inverters to have the capability and provide the service of providing oscillation damping control. And then we refer to that as IBR POD, power oscillation damper, and there are different ways to do that depending on also on the inverter technology and on the inverter controls. So for example, if we have a grid following inverter, if you are familiar with the term, in order to provide oscillation damping, we would need an auxiliary control, which again is, we refer to it as a POD control that basically has to be embedded with the other controllers and do active and reactive power modulation. So we have tested that, we have implemented such controllers, we have integrated that with the WEC generic IBR models, and we have shown how an auxiliary POD control for grid following inverters can be used to mitigate oscillations. Of course, it has to be tuned appropriately, but that's a different story. Now, similar thing can be done with grid forming, but here what we have been investigating is the capability of the inherent controls of grid forming to provide oscillation damping. So in this case, we have seen that we don't need an auxiliary control, we don't need an additional control on top of the other primary and outer and inner control loops that an inverter typically has. With grid forming inverters, we can rely on the primary controllers. It can be Droop, virtual synchronous machine, virtual oscillator, whatever that grid forming primary control is, we can rely on that to provide oscillation damping. Again, the extent to which the extent of the oscillation damping and that it can be provided it depends a lot on the system, depends on the parameters. So it needs a lot of, it would need some tuning, and of course, if there are other services that we are asking the grid forming inverter to provide, you know, there will be constraints. But again, we have seen that grid forming inverters have the inherent capability to provide oscillation damping. And last but not least, I wanted to close this presentation with this concept that we are promoting as a grid damper, the adaptive power grid oscillation damper. So it's basically a combination of what I presented today, basically designing controllers and not only the controller itself, but the whole design scheme and the whole design process of how to select these sensors and the inputs to the controller, the actuators, how you parameterize and how you tune the controllers depending on the specific application, different kinds of oscillations, natural oscillations, forced oscillations, subsynchronous oscillations, local versus wide area control, and most importantly, something that a controller that is adaptive with regards to the or with respect to the operating condition, because again we start seeing more and more that the operating conditions now in the system with variability and uncertainty from the inverter-based resources there are large variations in the operating conditions. So the controls that we design, they have to be adaptive to that operating condition. So with that, I'll close the presentation, and I'll be happy to respond to any questions or comments.
Okay, for the question, maybe first let's go to the people online. So any question all on team? If you have question, please unmute yourself and ask question from Evangeline. No? If not, okay, let's go by people in the room. So
I have a question.
yeah, go ahead.
So in the first part where you're using wide area measurements for damping the natural oscillations, you use a lead lag compensator. So are you using frequency response of the system to design the controller?
Yes, so the input signal is the frequency measurements from the PMUs. We have also tested other cases where we have voltage or active power as input measurements. But we have seen that frequency in this case is the most effective and more, I would say, practical in terms of the implementation. Yeah.
No, but how are you designing the lead lag controller? Are you using the frequency response of the system, like the body plot?
You mean for the design? Yes, for the design, yes. There is a design process, as I mentioned in this figure. So basically, yeah, we depending on after we select the optimal input signals and the optimal actuator, yeah, we go through this design, body plots, frequency response, and based on that, we calibrate and we calculate the parameters of the lead lag structure.
But how are you estimating the body plot of the system in real time? Because you say that this is an adaptive controller. So that would mean that you need to have the information of the frequency response between the actuating point and the signal of choice on the runtime, on real time issue. So how are you estimating that?
Yeah, so in real time, we don't do the body plot analysis. In real time, what we do is we use system identification. So basically, based on the input measurements, we use system identification to update the parameters of the transfer function that we use for the design of the controller. And once we update the parameters of the transfer function through the system identification, then we do the calculations to update the parameters of the controller. So that's here what is referred to as measurement-driven model. So again, we use the PMUs in real time to update the transfer function, which is the model through system identification. And then once we have that, we have a process that we update also the parameters of the control based on the parameters of the transfer function, which represents the closed loop system.
Are you using ambient data or ring down data for system identification?
We use ambient data. But we are also using a probic signal. So basically, we inject periodically a probic signal that, you know, because relying purely on the ambient data, there might be the signal to noise ratio might not be sufficient. So we use a probic signal that is relatively small in magnitude, but sufficient enough to perturb the system as much as we need to basically do the system identification. And that's, again, part of the offline analysis that we do also with the hardware in the loop to decide, you know, what would be the appropriate signal and the size of the probic signal so we can have satisfactory results when we do the system identification.
I see. And how often do you probe the system?
That's a user-defined parameter. We can do it every few minutes, every few hours, depending on how the operating conditions are changing. Actually, in the tool that we have implemented for Terna, that I was showing before, that we are now going through the field deployment, we have in the tool the option for the system operator to trigger that probing. So it is part of the GUI in the tool that the operator can press a button and say that I want now to inject a probing signal and do the system identification. So it can be set periodically, or it can be manual triggered. There are different options here depending on how complex you want the process to be.
Thank you. Thank you very much.
Yeah, thank you. Very good question.
Hello.
Yeah.
Can anyone hear me? Oh, great. Thank you. Professor, I really appreciate this presentation. My name is Jenny. I am a power systems engineer at PNNO. And my question to you is, considering that this controller is dependent on measurements and all that, how is it or how does it react to measurement errors or cases where the measurement data is just not available, maybe because there's communication link failure or maybe just random events? How will this react to that?
Yes. Yeah, good question. So as I said, we are taking this into account with different advanced modules that we have as part of the control. So we have a delay compensator that basically we rely on the synchronization of the PMU data, or on the time synchronization of the PMU data to try to calculate or estimate the time delay so we can compensate that. We have a logic to basically handle missing data and basically eliminate the impact of missing data. If you have failures, either from a PMU or an equipment as an actuator, we have a supervisory control that basically is looking at the condition of the PMUs and also the actuators, and can switch between different PMUs or different actuators, again, if there is a failure in one of those. So we have basically primary PMUs and backup PMUs and primary actuators and backup actuators, if you want, depends on the design. So we have considered all these things, and we have done a lot of testing in hardware in the loop, and we have demonstrated what is the impact of different operating conditions. We have seen that, for example, for missing data, the controller can handle up to 50 or 60% of missing data with acceptable performance. In terms of PMU failure or actuator failure, we have heuristics and we have logic, as I said before, where basically if one of them is missing, we allow some kind of delay, and if the issue persists, then we are switching to the backup signals. And yeah, in general, we have shown that we can handle these conditions, and we plan or we expect to see the performance of the controller in real time based on the field implementation. But in the hardware in the loop, we have shown that we can handle these situations.
Okay, thank you. Professor, one follow-up question to that is, it seemed from the answer that you gave, and I'm very satisfied with that. That is not to say that I'm not satisfied, but you seem to have talked about missing data and delayed data. How about the case of erroneous data? So you got the data, it was not delayed. How do you know that that erroneous data does not affect the outcome of your control?
Yeah,
I think I'm missing something there.
We have
yes,
some
please
heuristics around that. Yeah, we have some heuristics about that as well. So we have thresholds that to basically kind of decide whether some data are good data or bad data. And then if we think that this is bad data, we have also heuristics that either we drop it and we don't need it, or we try to replace it. We have papers with where we have done this analysis, and we have reported the results through, again, simulations on hardware in the loop. To what extent you can handle missing data or bad data. So if you are interested, I can provide you the links of those papers, and you can see the details. Of course, you know, if the quality of the data is really bad, if you have huge delays, if you have you know, very erroneous data with measurements that don't make sense, the best option is to deactivate the controller. It's better to deactivate the controller until you fix those issues. But typically, this is not happening. Typically, what we have seen is that if the system is designed well, and unless something unexpected happens, the delays or the amount of missing data or the bad data, they are tolerable. And the technology we have within the controller to handle those is acceptable. The performance of the controller is acceptable.
Thank you very much. I appreciate that.
Thank you.
I have a quick clarification question. So, did you mean that Terna is going to use the adaptive control that you just described? So, are they planning to set up in their system?
Yes, that's the objective. We are not there in terms of the adaptive yet. I have to say. So basically, we have installed. We have the software in the control center. We have all the hardware in the substations. We have tested that with one actuator and with predefined parameters of the controllers and tune controller for a specific oscillation mode. So this has been done and tested. The adaptive performance, this is something that we are working actually right now. We are looking how to implement this system identification in real time for the Terna system and update the parameters depending on the oscillation mode and all these things. So yes, the interest is to implement that, and hopefully we will have more to show probably next year. But in terms of the basic implementation and design, this has been already done. Yeah.
So you see that adaptive controller being implemented in near future then?
Yes, that's the objective. Yes.
Thank you.
I have another question. So how are you choosing the location of actuation and the measurement that you're using for the feedback? Because for the actuation, you need to have high controllability against that mode. So how are you choosing those?
So it's basically on observability and controllability analysis. So we get the system model for different operating conditions, and then we do controllability and observability analysis for those locations. And there are many ways to do the controllability and observability analysis. We have a specific method that we are using. And again, I can send you papers if you're interested. And yeah, that's how. Of course, the other thing is that, you know, we also need to consider some, especially for the actuators, we have to consider some practical considerations. So, for example, even if the theoretical analysis shows that, you know, a specific location has high controllability, maybe the utility doesn't have an equipment or doesn't own the equipment in that area, so we cannot use it. So again, there has to be also some practical considerations on whether we have access to that equipment, whether the utility wants to use that equipment, and things like that. So it is a compromise, I would say, between theoretical analysis and some practical considerations, if that makes sense.
Thank you for that. I have a follow-up question on ambient database system identification. So for that, we need the information of both the inputs and the outputs for system identification. So if we are doing ambient database system identification, what are the inputs that we are using and what are the outputs for the model? We need information of both the inputs and the outputs.
Yes. So basically, the input is the frequency, the output is the control signal, right? So that's how we do the system identification.
The frequency from the point of actuation.
The frequency, no, the frequency is the input signal. The point of actuation is the control signal.
I see. So for system identification, the input that you're using for the system identification to estimate the model, that is the frequency, right?
Yes, the frequency from the PMUs, yes.
From the remote PMUs?
Yes, from the remote PMUs.
Okay, and the outputs that we're using for system identification, what are those?
The control signal.
I see.
The active and reactive power that we do the modulation.
I see. Okay. Thank you very much.
So just as a kind of related question, so how the topology changes considered in all this identification? I assume that if you have topology change, so all of the observability and controllability will significantly change it. Or even during your adaptive control, how often do you update the model? Those kind of things, if you can comment on that, would be nice.
Yeah, so we don't have a network model as part of the controller. As I said, we do this, we calculate the transfer function with the system identification. Now, if there are topology changes, that will be reflected in the modes of the system. So that will be reflected in the transfer function parameters that you calculate. But typically, I would say topology doesn't affect too much the oscillation modes. The oscillation modes are kind of they are more dependent on the operating condition in terms of the power flows, which of course the topology plays a role, but yes, this is reflected into the transfer function when we do the system identification.
Okay. Thank you.
This is not much of a technical question. So, in a case when we have to implement the technology of supporting the frequency damping with the battery, the BESS technology, like who does the implementation? Like, is it the generator? Is it the PUD? Is it who oversees this? Is it the ISO? Or who puts this on the system?
Yeah, well, so that depends on many things. First of all, depends on in which system this is happening and which utility is involved with. If there is a system operator in that area or not, who owns the battery. So I would say it has to be a collaboration between the utility, the transmission owner, the generator owner, the battery owner, and the operator. So it has to be a combination of that. And one thing to clarify is that specifically for batteries, that here we are not proposing to a utility to install a battery with the oscillations damping control as a use case. We are saying that There are other use cases for batteries that I would say they would be more profitable for a utility, but we consider this oscillation damping as an additional service, as an additional capability that a battery can offer once you have it there. So it's like an extra service that the battery can provide. And again, we acknowledge that there are other use cases that are more profitable and other reasons why would someone install a battery into a system.
Okay, thank you. I mean, that probably would have been my second question, because like you said, as the battery system owner, like I want to use my battery to generate active power, not reactive power, because obviously that pays more than using it to generate the reactive power. But like you said, if it's an add-on, then it's yeah, I think it's okay.
Yes, but for battery, you can use both active and reactive power to do the modulation here and the oscillation damping. You don't have to use only reactive power with the battery. You can use only active power. But again, yeah, like you said, the energy provided will be a very small amount. It's not something that will, provide any major economic profit to the owner. It's more of a reliability service that we are providing, again, as extra as an extra capability.
All right, thank you.
Question?
I have one question. So I just wanted some clarification on your results for the 70K test system. So first, you have checked for one big battery and like 12 smaller batteries. So my first question is, like, those smaller batteries, I'm assuming they are peppered throughout the nodes and not just one single node. And was there any meaningful difference between these two times with the bigger battery and with smaller batteries?
No, and the reason why we did this scenario is to investigate whether there could be any control interactions by having multiple controllers and modulating different actuators. And yeah, we didn't see any major differences between the two scenarios. There are some slight differences because, like you said, in one scenario we had one big battery in one location, in the other one we had multiple smaller batteries in different locations, close to each other, but not all of them in one specific location. So the results are a little bit different, but again, the objective was to investigate whether there could be any control interaction, which we didn't see. So that was the main conclusion from these specific scenarios.
Okay. Yeah. Thank you. Yeah.
Thank you. I think the last question, anyone want to ask or not? Good. Everybody is good? Okay, thank you, Evangelist. That was really very informative talk. We really appreciate that. So we learned a lot this presentation. Thank you. And maybe one more. Thank you.
Thank you again. And yeah, for those who are involved with PSERC, I will most likely be in Atlanta for the next PSERC meeting. So maybe I will see some of you over there.
Oh, that's perfect. So see you sometime soon. So yeah, good. Yeah, I'm sure there are several students will attend that. They have ongoing project at PSERC. So, yeah. Okay, good. Have a great day and see you soon. Okay, thank you.
Yeah, thank you very much. Yeah.
Thank you. Bye.